Okay, I don't really want to show you, so I'm going to go to the student view here. Sorry about that. Now I'm wasting your time doing this. There we go. Come on, Wiley Plus, help your brother out here. Hurry up. Okay, let's just take a look at these problems. How do they work? All right, just so you get an idea of how we're, okay, so human lungs, now this looks like it might be kind of complicated. All right, human lungs can function satisfactorily up to a limit where the pressure difference between the outside and inside of the lungs, okay, where the pressure difference on the outside and the inside of the lungs is 1/119th of an atmosphere. If a diver uses a snorkel for breathing, how far below the surface can she swim? Assume the diver's in salt water whose density is 1,041 kilogram. Okay, so we need to know the height that they can go down, okay, for a pressure difference. So if the pressure difference on their lungs between the outside and the inside of their lungs, we're going to assume their inside of the lungs is at 1 p is one, because it's not filled with water or anything. In other words, now the volume has gone way down because the pressure is going to stay the same. The pressure inside is going to stay the same, but it's going to probably have shrunk just a little bit. So the pressure on the inside is the same as the one on the outside. So here's what I'm saying, and I think I'm going to get this right. So I better do this correct. All right. So 1/19, 1/19 is the factor of the pressure difference, and salt water is the rho salt water is equal to 1041 kilograms meters cubed. Okay, now I'll let you in on the secret. Here we go. Okay, so this person's swimming underwater here. Let's do it down here. All right, so swimming underwater, and let's just draw a circle of their lungs. All right, so their lungs are pushing out this way. Okay, and then how deep can they go? All right, plus we got this pressure up here too. It's going to be pushing down. And this pressure differential, which this pressure is going to equal this pressure, so I'm going to say that those cancel out. And so that's what I'm going to go with. And if I'm wrong, I'll erase this, and this never happened. All right. But if I'm right, then we're on. Then we're going good. And so we want to know this height. Well, what's the pressure that they're feeling? The change in pressure. Okay, so the change in pressure is equal to P1 plus P2 plus P of the salt water minus P1 inside the lungs is equal to 1/19th of a Pascal of an atmosphere, which is 1.013 times 10 to the fifth pascals. Okay, that's what they're saying. And this change in pressure, I've already said, is rho GH. I think I might be overthinking it. I might be overthinking it. Because I think I need to add that pressure too. But anyway, so let's just go with this. So the change in pressure is going to equal 1 divided by 19. That's what they mean by the ratio. 1/19 times 1.013 times 10 to the fifth pascals is equal to 1041 times 9.8 divided by h. So we'll take 1 divided by 19. Get that one out of the way. Times 1.013 second e to the fifth divided by double parentheses 1041 single parentheses 9.8. Height is equal to 0.5226 meters. That's what I think it is. Okay, let's go back and see, because I didn't leave it out there. So 0.5226 units meters. Submit. Hey! That's right. I'll be darned. Let's look at 34. We're on a roll now. We are on a roll. What's 34? Oh, this is just a simple Pascal problem, Pascal's principle. And we want the ratio of the radius of the plunger to the radius of the piston. So plunger over piston. Okay, here's the input piston, here's the output plunger. I always think of the plunger as this one, but okay, so it's plunger over piston. All right, so we're going to call this one A1, or this one will be P1 or F1, because remember Pascal's principle says the pressure at one end is equal to the change in pressure at another. Okay, Pascal says this. So for this problem, the pressure on 1 is equal to the pressure on 2, and you got force over area. Force 1 over area 1 is equal to force 2 over area 2. Okay? All right, and all we're looking for, this is the plunger, this is the piston. Because I'm going with the big guy on the big chair divided by the dentist's foot over that little plunge, over that little input piston. Okay? And so here's what I got. I mean, all they want the ratio of A1 to A2. Well, what's that equal? I'll multiply both sides by A1, say, divide both sides by F2. There you go. I know that one will work, so I'm not going to bother. Now let's go to 40. Oh, this is one of my favorites. This is one of my favorite problems of all time. We'll probably do this one in class. We'll just do in class. So 40 in class. So let's look at 43 because I think we got some bonus time. So let's look at problem 43. Hopefully it's a continuity type thing. A duck is floating. Oh, no, this is another Bernoulli thing. What's the density of the duck? Well, let's take a look at that. We can do this one really quick. Say a duck is floating on a lake with 20% of its volume out of the water. Okay. Okay, so a lot of its volume, 80% of its volume is in the water. Okay. What is the average density of the duck? What the heck? Well, here's what's going on. Let's take a look at what's going on here. I might have to pause and I can't. The trouble is, once I start with the QuickTime video, it's QuickTime. I can't pause it and then do the work and then come back and go, okay, I got it now. So I'm just having to wing this, thinking I'm a genius boy and I can just wing it. So we're going to pretend the duck is like a ball, all right? And so here he is. Here's our duck. Now this much of him is in the water, okay? All right, so his weight pushing down, this is P1 pushing down on the air is pushing down on him here, right? Well, there's no force pushing down on him there. The only force that's happening here, so the sum of the forces is equal to 0, which is equal, because see the pressure is isometric all the way around, so we don't need to worry about that one right now. All right, so I mean if we wanted to figure out what the pressure was down here, we'd include that, but we're not doing that. So the sum of the forces, so the only force is equal to mg minus of the duck minus the buoyancy force. So the buoyancy force is equal to and in mass of the duck, the buoyancy force is equal to rho of the water times the volume of the water displaced times G. Okay, and the mass of the duck is equal to rho of the duck times the volume of the duck times G. All right? So we're figuring out the rho of the duck. And we've got it. We've got it. It's one of those, you just got to trust the math. So we've come up with mg. So the mg of the duck is rho duck, which is what we're after. Volume of duck times g is equal to, this mg is equal to rho of water, which we know, times 0.8 volume of duck, so I don't know, times g. So it actually turned out to be, some of you probably just use common sense. Well, the duck is 80% the buoyancy of water, is 80% the density of water. That's why it floats. And you are absolutely right. Because look, the volume of the duck cancels, the 0.8 doesn't, the g cancels, and all we're left with is the rho of the duck, volume of the duck, is equal to rho of water times 0.8. So the duck is equal to 800 kilograms per meters cubed is its thing. Pretty cool because we know the rho of water. All right, we'll stop here.